Linear Algebra 2, Tutorial 10, Repetition. The aim for today is to solve a number of problems which cover all the major parts of our course. Problem 1. Let V be the subspace of the linear space of all 2 times 3 matrices with real coefficients, which is generated by the matrices M1, which is 1, 0, 1, 1, 0, 1, M2, which is 303, 303, M3, which is 010, 020, M4, which is 111, 121, M5, which is 2 minus 1, 2, 2 minus 1, 2, and M6, which is minus 1 to minus 1, minus 1, 4, minus 1. Part A. Find a basis in V consisting of some of these matrices. Part B. Determine the coordinates of all of these matrices in this basis. Part C. Determine whether the matrix n, which is equal to 1, 2, 3, 3, 2, minus 1, belongs to V, and, if this is the case, determine the coordinates of n in the above basis. Solution. In the linear space of all 2 times 3 real matrices, we have the standard basis, denoted by bold E, which consists of the matrix units E11, E12, E13, E21, E22, and E23. Recall that the matrix unit Eij has 1 as the entry in the intersection of the row I and column j, and all other entries are equal to 0. The coordinates of all the matrices which are mentioned in the formulation in this basis are, so the coordinates of M1 are 1, 0, 1, 1, 0, 1. So we should just read the matrix left to right, top to bottom, 1, 0, 1, 1, 0, 1. So the coordinates of M2 are 303, 303. The coordinates of M3 are 010, 020. The coordinates of M4 are 111, 121. For M5, we get 2 minus 1, 2, 2 minus 1, 2. For M6, minus 1, 2 minus 1, minus 1, 4, minus 1. And for N, we get 1, 2, 3, 3, 2, minus 1. To solve our problem, we need to write all these vectors into one matrix. So we write the coordinates of these vectors as columns into one matrix. We separate the coordinate vectors for M1, M2, and so on up to M6 from the coordinate vector for N by a vertical line, and we get this huge matrix. And now we need to reduce this matrix to a row echelon form using Gauss elimination. So first of all, let us note that the rows 3 and 4 are the same, so we can just delete row 4. So now when we look at our matrix, we see that rows 1, 3, and 5 are almost the same. They only differ in the last coordinate. So we multiply row 1 with minus 1 and add to row 3 and row 5. And similarly, we multiply row 2 with minus 2 and add to row 4. And then when we compute everything, we get the following matrix. So the first row will remain the same. The third row was almost the same except for the last coordinate, where we will get 3 minus 1, which is 2. And the fifth row was almost the same except for the last coordinate, where we will get minus 1, which is minus 2. And in row 4, we see that it is twice row 1 except for the last coordinate. So in the last coordinate, we will get minus 4 plus 2, which is minus 2. So this is the matrix which we obtain using our operation. And we see here that the matrix on the left-hand side before the vertical line, it has 2 non-zero rows. It's in the row echelon form, so it has rank 2, while the matrix together with the last column, so the complete matrix, has obviously rank 3. We will have a non-zero element here. And this means that the vector n does not belong to the subspace V. So the leading elements in our matrix here to the left are in columns 1 and 3, and this means that the matrices M1 and M3 form a basis of our vector space V, and we denote this basis by bold little m. And then the first two coordinates in each column, for M1 and so on up to M6, give the coordinates of these matrices in the basis consisting of M1 and M3. So M1 has coordinates 1, 0, M2 has coordinates 3, 0, M3 has coordinates 0, 1, M4 has coordinates 1, 1, M5 has coordinates 2, minus 1, and M6 has coordinates minus 1, 2. And this completes problem 1. Problem 2. Let F be a linear map from R3 to R3, which is given by the projection onto the plane given by the equation x1 plus x2 plus x3 is equal to 0, along the vector v, which is the vector 1, 2, minus 2. So we have a linear operator which projects onto this plane along this vector. And we need to determine the matrix of this linear operator in the standard basis. Let us start our solution by determining some basis in our plane, which is given by an equation. Here we can observe that the vectors 1, minus 1, 0 and 0, 1, minus 1 obviously belong to the plane, and they are obviously linearly independent because they are not proportional. So these two vectors, they form a basis in a plane because a plane has dimension 2. And then we have our vector v, which we now denote by W3, and this vector doesn't belong to the plane. So it is linearly independent with the vectors W1 and W2. So together, the vectors W1, W2, and W3 form a basis in R3, which we denote by bold W. For the elements in our basis, we have the following. F of W1 is equal to W1 because W1 already belongs to the plane and we don't need to project anything. Similarly, f of W2 is equal to W2 because W2 already belongs to the plane. Finally, f of W3 is equal to 0 because the projection is along the vector W3. So W3 goes to 0. This means that the matrix of F in our basis W is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 0. This is a diagonal matrix. So this is the diagonal matrix with 1, 1, 0 on the main diagonal because of this computation. Now we want to use the base change formula to determine the matrix of F in the standard basis. So this matrix is equal by the base change formula to the transformation matrix from E to W, then the matrix of F in W, and then the transformation matrix from W to E. So TEW is a transformation matrix from E to W. It consists of the coordinates of the basis vectors W1, W2, and W3 in the standard basis, written as columns. And TWE is a transformation matrix back, which is the inverse of the transformation matrix forward. So the transformation matrix from E to W is the matrix, if you read it column-wise, 1, minus 1, 0, this is W1, then 0, 1, minus 1, this is W2, and then 1, 2, minus 2, this is our vector W3. So let us compute the inverse of this matrix. This will be the transformation matrix back. So we write this matrix, vertical line, and the identity matrix, and we reduce the left-hand side to the identity matrix using Gauss elimination. So we add row 1 to row 2 to kill this minus 1. So row 1 and 3 remains the same, and row 2 becomes 0, 1, 3, 1, 1, 0. Now we can add row 2 to row 3 to kill this one. Rows 1 and 2 remain the same, and row 3 becomes 0, 0, 1, 1, 1, 1. Now we can use this one to kill 3 and 1. So we subtract row 3 from row 1, and we subtract 3 times row 3 from row 2. So the row 3 remains the same, Row 1 becomes 1, 0, 0, should be 0 here, 0, minus 1, minus 1, 0, 1, 0, minus 2, minus 2, minus 3, and row 3 is 0, 0, 1, 1, 1, 1. Consequently, the transformation matrix from W to E is the matrix 0, minus 1, minus 1, minus 2, minus 2, minus 3, 1, 1, 1. So now we can use the base change formula. So the matrix of F in the standard basis is the product of the transformation matrix from the standard basis to W times the matrix of F in W times the transformation matrix back. And now we write the product of these three matrices. So the first transformation matrix is 1, 0, 1, minus 1, 1, 2, 0, minus 1, minus 2. The matrix of F in W is a diagonal matrix with 1, 1, 0 on the diagonal. And we just computed that the transformation matrix back is 0, minus 1, minus 1, minus 2, minus 2, minus 3, 1, 1, 1. We first multiply matrices 2 and 3, and we get simply the first two rows of the third matrix. So 0, minus 1, minus 1, minus 2, minus 2, minus 3, 0, 0, 0. Now we multiply these two matrices, and here we get just the first row, 0, minus 1, minus 2. Here we get row 2 minus row 1, which is minus 2, minus 1, minus 2. And finally, minus row 2, 2, 2, 3. And here is our answer. The matrix of F in the standard basis is the matrix 0, minus 1, minus 1, minus 2, minus 1, minus 2, 2, 2, 3. And this completes problem 2. Problem 3. Let G be the linear map from R4 to R4, which has the following matrix B in the standard basis. The matrix B is the matrix 1, 1, 2, 2, 2, 2, 4, 4, minus 1, minus 1, minus 2, minus 2, minus 2, minus 2, minus 4, minus 4. Without the computation of the characteristic polynomial, show that both 0 and minus 3 are eigenvalues for this matrix. Determine the geometric multiplicities of these eigenvalues and find some bases in the corresponding subspaces of eigenvectors. Solution. To show that 0 is an eigenvalue, we need to show that there are some eigenvectors, non-zero eigenvectors for this eigenvalue. And this means that we need to solve the homogeneous system of linear equations whose matrix is B minus the eigenvalue times the identity. So since the eigenvalue is 0, this is just B. So we need to solve the homogeneous system of linear equations with matrix B. So we need to reduce B to a row echelon form using Gauss elimination. It is very clear that all rows of B are linearly dependent, so we can delete 3 of them to get the matrix 1, 1, 2, 2. This is our row echelon form. So we have one leading element in column 1, and this means in particular that the rank of the matrix is 1, and so the homogeneous system of linear equations has 4 minus 1, which is 3 linearly independent solutions. So in particular, this shows that 0 is indeed an eigenvalue, and also that the geometric multiplicity of this eigenvalue is 3. To concretely solve the system, since our leading element is in column 1, we take x2, x3, and x4 as free variables, and then our only equation becomes x1 is equal to minus x2 minus 2x3 minus 2x4, and we add the trivial equations for the free variables. x2 is equal to x2, x3 is equal to x3, and x4 is equal to x4. Now we can write this in the vector form. So the vector x1, x2, x3, x4 is equal to x2 times the coefficient vector minus 1, 1, 0, 0. So it comes from here, minus 1, 1, 0, 0. So the next coefficient vector is minus 2, 0, 1, 0. So we have plus x3 minus 2, 0, 1, 0, and then plus x4 minus 2, 0, 0, 1. And this implies that our coefficient vectors, so v1, which is minus 1, 1, 0, 0, v2, which is minus 2, 0, 1, 0, and v3, which is minus 2, 0, 0, 1, They form a basis in the linear space of all eigenvectors with eigenvalue 0. Next, we need to treat the eigenvalue -3. So to show that -3 is an eigenvalue, we need to show that there are eigenvectors, or in other words, that the homogeneous system of linear equations whose matrix is B minus -3 times the identity has a non-zero solution. So we take this matrix and reduce it to a row echelon form using Gauss elimination. So the matrix itself is 4, 1, 2, 2, 2, 5, 4, 4, -1, -1, 1, -2, -2, -2, -4, -1. First, we put row 3, because it has -1 here, as row 1 and push rows 1 and 2 down. And we also multiply it with -1 to have 1. So the first row becomes 1, 1, -1, 2. And then we have the original row 1, original row 2, and original row 4. So now we can use this 1 to eliminate all elements in its column. So we multiply row 1 with -4 and add to row 2. We multiply row 1 with -2 and add to row 3. We multiply row 1 with 2 and add to row 4. So row 1 remains the same, and the rest of the matrix becomes 0, -3, 6, -6, 0, 3, 6, 0, 0, 0, -6, 3. So now we swap rows 2 and 3 and divide row 2 by 3. So row 2 becomes 0, 1, 2, 0. And now we can use this 1 to kill everything else in its column. So we subtract row 2 from row 1, and we multiply row 2 with 3 and add to row 3. Rows 2 and 4 remain the same. Row 1 becomes 1, 0, -3, 2, and row 4 becomes 0, 0, 12, -6. So now we see that rows 3 and 4 are linearly dependent, so we can delete one of them and divide the other one by 3, and so we get that row 3 becomes 0, 0, -2, 1. So now we treat this 1 as a new leading element, and we use it to kill 2 here. So we multiply row 3 with -2 and add to row 1. And in this way, we get the matrix 1, 0, 1, 0, 0, 1, 2, 0, 0, 0, -2, 1. And here we have the leading elements in columns 1, 2, and 4. So this means that the rank of our matrix is 3, and hence our homogeneous system of linear equations has one linearly independent solution. So 1 is equal to 4 minus 3. So in particular, this means that -3 is indeed an eigenvalue, and that the geometric multiplicity of this eigenvalue is 1. And from this matrix, since our leading elements are in columns 1, 2, and 4, we take x3 as a free variable and obtain the system from the first row. x1 is equal to minus x3, second row x2 is equal to minus 2x3. For x3 we have the trivial equation, and from the third row x4 is equal to 2x3. And hence the coefficient vector v4, which is equal to -1, -2, 1, 2, forms a basis in the linear subspace of all eigenvectors with eigenvalue -3. And this completes problem 3. Problem 4 showed that the second order surface in the Euclidean space E3, given by the equation x squared minus y squared plus z squared minus 4xz is equal to 1, is a rotational surface. Determine the type of this surface, the rotation axis, the minimal distance from the surface to the origin, and all points on the surface that are closest to the origin. Solution. We start by writing down the matrix in the standard basis for the quadratic form which defines our surface. So the coefficient at x goes into position 1, 1, the coefficient at y goes into position 2, 2, the coefficient at z goes to the position 3, 3, and the coefficient at xz is divided by 2, and so -2 and -2, they go in positions 1, 3, and 3, 1. So now we have this symmetric matrix, and we need to determine the eigenvalues of this matrix. So to determine the eigenvalues, we compute the characteristic polynomial. So we take our matrix and subtract x on the main diagonal, and we need to compute the determinant for the matrix 1 minus x, 0 minus 2, 0 minus 1 minus x, 0, minus 2, 0, 1 minus x. So this is a product of the determinant of this 1 times 1 matrix, which is minus 1 minus x, times the determinant of this 2 times 2 matrix, which is 1 minus x squared minus minus 2 squared. Since this second factor is a difference of two squares, we can write it as 1 minus x minus 2 times 1 minus x plus 2. So we'll have minus 1 minus x times 3 minus x. And now when we put all this together, the characteristic polynomial becomes 3 minus x times minus 1 minus x squared. This means that we have two eigenvalues, lambda 1, which is equal to 3, with algebraic multiplicity 1, this is this factor, and lambda 2, which is equal to minus 1, with algebraic multiplicity 2, this is this factor. Since we have an eigenvalue with algebraic multiplicity 2, this means that our surface is a rotational surface. Also, we know that we have one positive eigenvalue, 3, and two negative eigenvalues, minus 1 with multiplicity 2. This means that our surface is a hyperboloid of two sheets. The maximal eigenvalue is 3, and so the minimal distance from a point on the surface to the origin is 1 divided by the square root of the maximal eigenvalue. So it is 1 divided by the square root of 3. To determine the rotation axis for our surface, we need to determine a non-zero eigenvector for the eigenvalue of multiplicity 1. That is for the eigenvalue lambda 1, which is equal to 3. Eigenvectors with eigenvalue 3 are the solutions to the homogeneous system of linear equations whose matrix is obtained from our matrix by subtracting 3 on the main diagonal. So we get the matrix minus 2, 0, minus 2, 0, minus 4, 0, minus 2, 0, minus 2. We immediately delete row 3 because it's equal to row 1. We divide row 1 by minus 2, and we divide row 2 by minus 4. And we get the matrix 1, 0, 1, 0, 1, 0. And for this matrix, it's easy to guess that the vector 1, 0, minus 1 is a solution. And since the multiplicity of this eigenvalue is 1, it's a unique linearly independent solution up to a non-zero scalar. And the rotation axis is exactly the line which is spanned by this eigenvector. So the rotation axis is the line consisting of all scalar multiples of the vector 1, 0, minus 1. The points on our surface that are closest to the origin should be exactly the eigenvectors of lengths, this smallest distance to the origin, which is 1 divided by the square root of 3, for our maximal eigenvalue. So we know one eigenvector, so all other eigenvectors are scalar multiples. So it is convenient first to norm V to get a normed eigenvector W, which is equal to V divided by the length of V. So the length of V is a square root of 1 square plus minus 1 square, so it's a square root of 2. So we have the normed eigenvector 1 divided by the square root of 2, 1, 0, minus 1. And therefore, the points that are closest to the origin are the points plus minus 1 divided by the square root of 3 times this normed eigenvector. And so these are the points plus minus 1 divided by the square root of 6, 1, 0, minus 1. And this completes problem 4. Here are some additional problems and questions. Question 1. In problem 1, consider the space of all 2 times 3 real matrices as an Euclidean space such that the standard basis is an orthonormal basis. Determine the orthogonal projection of the matrix N onto the subspace V. Question 2. In problem 1, consider the space of all 2 times 3 real matrices as an Euclidean space such that the standard basis is an orthonormal basis. Find some orthonormal basis in the orthogonal complement to V. Question 3. Solve problem 2 with v replaced by the vector v prime, which is minus 2, 1, 2. Question 4. In problem 3, determine whether the linear operator g is diagonalizable. If this is the case, determine the diagonal form and the transformation matrix to the corresponding eigenbasis. Question 5. In problem 4, it is possible to change the coefficient at y square such that the new surface will again be a rotational surface. There is one other choice for coefficient such that we get a rotational surface. Find this new coefficient and solve an analog of problem 4 for this new surface. Thank you very much, and this completes the course.